Welcome back to The Explainer. I am absolutely thrilled to have you here today because we are going to look under the hood of a technological marvel that has literally shifted the landscape of our modern world. We're unpacking the true, unglamorous, yet utterly fascinating story behind ChatGPT. And to do this, we're relying on a brilliant investigative deep dive from Tech Reader magazine written by Aaron Rose. So if you've ever found yourself wondering what it actually took to make this AI functional, well, you are definitely in the right place. Today, we're going completely off the standard narrative. We are going to totally shatter that popular myth that ChatGPT was this sudden miraculous breakthrough where some lone genius just cracked the code overnight in 2022. I mean, it's a super compelling story, right? But it just isn't true. The reality is way more complex, much more structural, and honestly, a whole lot more impressive. I love this quote. Building ChatGPT wasn't a research problem, it was an industrial one. The underlying math and the transformer architecture itself, that was already established. Almost any competent machine learning engineer could code up the basic architecture in, say, a few hundred lines. The true bottleneck, the actual mountain they had to climb, was a massive industrial challenge. They had to build a factory of unprecedented scale. Just think about the timeline of this industrial build-out for a second. It's incredibly revealing. The underlying transformer paper was published by Google way back in 2017, so the core idea was essentially settled. But ChatGPT didn't actually launch until November 2022. That 5-year gap wasn't just a lapsed time where people were sitting around twiddling their thumbs. That was a grueling 5-year span of invisible, heavy-duty back-end engineering. It was the absolute ground-up construction of pipelines and systems that simply had never existed before. To really grasp the scale of this achievement, we're going to break down this massive machine piece by piece. First, the data supply chain, then the infrastructure cathedral, followed by the behavior problem, and finally, the simple front door. Let's dive right in. Section 1, the data supply chain. This is all about figuring out how to feed the machine. Before you can even begin cooking your AI model, you have to figure out how to feed it the entire internet. 45 terabytes. That is the approximate size of the filtered text dataset they use to train GPT-3. And remember, this isn't just a big hard drive crammed full of random documents. This is 45 terabytes of text that has already been scrubbed, cleaned, and refined. Just think about the sheer mind-boggling volume of human language that actually represents. But you can't just dump 45 terabytes of raw text into a model and hope for the best. There's a really unglamorous heavy-lifting supply chain pipeline required here. First, web crawlers collect raw text at an unbelievable scale. Second, heuristic filters have to throw out all the low-quality garbage and harmful content. Step 3 is absolutely vital, deduplication. See, if you feed an AI the exact same paragraph 10 times, it just memorizes it instead of learning how language actually works. And finally, step 4, converting it all into a vocabulary the machine can actually use. That final, critical step of the pipeline is called tokenization. You know, transformers don't actually read English words. They read tokens, these compact numerical fragments. A single word might be broken into 2 or 3 tokens. Heck, even a space or a punctuation mark gets its own number. The engineers had to invent an incredibly efficient way to compress the infinite, messy variety of human language, foreign words, technical jargon, slang, you name it, into a compact numerical vocabulary that wouldn't completely overwhelm the computers. Moving right along to Section 2, the infrastructure cathedral. The sheer hardware scaling here is just wild. Once you have the data tokenized, you have to actually train the model. And that introduces a severe hardware nightmare called model parallelism. GPT-3 had 175 billion parameters. It is physically impossible to fit a model that immense inside the memory of a single GPU. So engineers had to invent brand new ways to split the model across thousands of GPUs running simultaneously. Different layers of the model lived on completely different pieces of hardware, all while the training data was also being split up. It requires this flawless synchronization that pushes the absolute limits of distributed systems engineering. And the pressure to get this right, it was immense. A single training run of GPT-3 cost an estimated $4 to $12 million in compute. Think about that. If those synchronized GPUs encountered a single critical bug, or if the learning process destabilized and the math went wonky a week into training, that meant millions of dollars were just instantly wasted, gone. The engineers had to develop a razor-sharp intuition to catch these problems early. But amidst all this massive financial risk, a monumental breakthrough happened in 2020.
OpenAI published a paper on neural scaling laws, proving that a model's performance improved predictably based on 3 specific variables: model size, dataset size, and compute budget. This was a total game changer, a complete paradigm shift. It turned AI development from a pure, expensive gamble into predictable engineering. You could actually calculate your results before you even ran the code. The math essentially guaranteed that if you just built the infrastructure big enough, the intelligence would emerge.
All right, section 3, the behavior problem. Because raw power isn't a product, and we need this thing to be safe. By 2020, they had a model that could write code and translate languages, but raw capability just isn't enough. A model that fabricates answers with total absolute confidence? Yeah, that isn't safe for the public to use. It had no real concept of truth, only what sounded plausible. The missing link to solve this was human preference, specifically a technique called RLHF, reinforcement learning from human feedback. This is the exact technique that shifted the AI from feeling like a random text generator to feeling like a helpful, trustworthy assistant. Let's walk through how this actually works because it was an astonishing shift in their engineering process. Step 1. Human annotators review pairs of the AI's outputs and rank which one is better, safer, and more helpful. Step 2. A separate reward model is trained on all those human rankings so it actually learns to predict what humans prefer. Step 3. The enormous base model is fine-tuned to maximize the score from that reward model. This wasn't some automated scaling trick. This was a slow, incredibly careful, human-intensive loop that fundamentally shifted the AI into a cooperative tool. Which brings us to our final section, Part 4, the simple front door, the chat interface. All of that meticulous, grueling back-end work brings us to the part of ChatGPT everyone actually uses. And the contrast in technical difficulty here is staggering. The data pipeline, that was an 8 out of 10 to build. The training infrastructure with those thousands of synchronized GPUs, a brutal 9 out of 10. But the chat interface, the little text box you and I type into, a 2 out of 10. It was, ironically, the simplest piece of the entire puzzle, but it mattered enormously because it completely abstracted away all of that 9 out of 10 complexity. You didn't need to know how to code. You didn't need an API key anymore. You just typed in plain English. And that brings us to the core thesis of this entire explainer. The math pointed the way, but the engineers built the road. ChatGPT is kind of like a Michelin-starred restaurant that also happens to run its own farms, its own supply chain, and its own private power grid. The recipe? That was the easy part. Building the physical infrastructure to serve 100 million people in record time, that took years of patient, unglamorous, and absolutely brilliant industrial engineering. So I want to leave you with a final thought to chew on. As we've just seen, scaling up the hardware caused entirely new capabilities to emerge organically, things nobody even explicitly programmed. As those capabilities continue to accelerate, how on earth will this invisible infrastructure scale to support the intelligence of tomorrow? That is exactly what we are going to explore in part 3 of this series. Keep your curiosity sharp, and I'll see you then.